Somewhere online right now, a headline is spreading that claims James Webb just filmed the actual death of Betelgeuse. Screenshots of it are getting passed around. Comment sections are half panicking, half arguing. People are asking if Orion is about to lose a shoulder. Here's the problem with that headline. Betelgeuse has not exploded. Nobody has photographed its final moments. Not Webb, not any other telescope on Earth or in orbit. But something real did happen this year that is stranger than the fake headline, better documented, and honestly more useful to understand. And yes, it does involve James Webb, just not in the way that headline wants you to think. If you are new here, this channel exists to take space stories like this one and actually check them against the science before repeating them. So if that sounds useful to you, subscribing helps more of these reach you. Now let's get into what Betelgeuse actually is, what really happened this year, and why so many people got fooled. Betelgeuse sits on the shoulder of Orion, one of the easiest constellations to find in the winter sky. It is a red supergiant, which is a very specific and very short-lived phase of a massive star's life. Estimates of its distance from Earth vary depending on the method astronomers use to measure it, ranging from around 550 to 700 light-years, with many recent papers clustering closer to the shorter end of that range. The measurement uncertainty is not sloppiness. Betelgeuse is close enough, and its atmosphere puffy and irregular enough, that pinning down an exact number has been a genuine technical problem for decades. The name itself carries almost as much history as the star. It comes from Arabic, most likely from a phrase meaning something close to the hand or the armpit of the central one, referring to Orion, though centuries of transcription between Arabic, Latin, and other European languages blurred the exact original wording, which is why you will still find slightly different explanations of the name depending on the source. Nearly every sky-watching culture had its own name for it. Ancient Egyptians associated it with Osiris. In Hindu astronomy, it is Ardra, tied to the storm god Rudra. Persian and Indian traditions both referred to it simply as the arm. That kind of cross-cultural attention only happens for a star that is genuinely hard to miss, and Betelgeuse ranks among the 10 brightest stars visible from Earth. It even ended up loaning its name, almost by coincidence of spelling, to a mischievous ghost in a 1988 Tim Burton film, which is honestly how a lot of casual viewers first hear the word at all, long before they ever learn. It is attached to a real dying star hundreds of light years away. What is not in question is the star's physical scale. Betelgeuse is somewhere around 700 times wider than the Sun, with some estimates pushing closer to 900, depending on exactly which part of its fuzzy, pulsating outer atmosphere you count as the edge. If you swapped it into the center of our solar system, its outer layers would stretch out past the orbit of Mars, and by some estimates, close to Jupiter. It burns with something like 100,000 times the Sun's total light output, despite having a surface temperature of only around 3,000 to 3,500 Kelvin, which is actually cooler than our Sun. That combination of enormous size and relatively low surface temperature is exactly why it glows that distinctive orange-red color you can pick out with your bare eyes on a clear night, and why ancient observers across unrelated cultures independently zeroed in on it. Here's the part that surprises people. Betelgeuse is young. Current estimates put its age at somewhere around 8 to 10 million years old, compared to our Sun's 4.5 billion years. But mass determines lifespan for a star, and Betelgeuse has somewhere around 20 times the Sun's mass packed into it. Heavier stars burn through their nuclear fuel far faster than smaller ones, because the pressure and temperature at their cores is so much higher. So despite being a cosmic infant next to our Sun, Betelgeuse is already in the final stretch of its life, fusing progressively heavier elements in its core on a timeline that keeps compressing as it goes, from hydrogen to helium to carbon, and eventually, in the very last stages, to elements as heavy as iron. Betelgeuse is also a variable star, meaning its brightness shifts over time in fairly predictable cycles. Its main pulsation runs about 420 days, layered on top of a longer cycle closer to 5 or 6 years. This variability was first documented in Western scientific journals by the astronomer John Herschel in 1836, who noted the star significantly outshining its neighbor Rigel in some years and fading well below it in others. There's also credible research suggesting Aboriginal Australian oral traditions describe the same variability in Betelgeuse long before Herschel's telescope ever picked it up, encoded in stories passed down through generations, rather than written star charts. Skywatchers, both professional and amateur, have tracked these fluctuations for well over a century and a half now, largely through organizations like the American Association of Variable Star Observers, whose members have logged nightly brightness measurements of Betelgeuse going back decades. That long, continuous baseline is part of why any sudden deviation from the established pattern gets so much attention from scientists immediately. And in late 2019, Betelgeuse gave everyone exactly that kind of deviation. Between November 2019 and March 2020, Betelgeuse dimmed further and faster than anyone had recorded before in that database. At its faintest, around the 7th to the 13th of February 2020, It dropped to roughly a third of its usual brightness, a drop large enough to notice just by looking up at Orion without any equipment. Longtime observers of the night sky were unsettled. Astronomers pointed serious instruments at it immediately, because a sudden dramatic dimming is exactly the kind of behavior a red supergiant might show in the years or centuries before core collapse. Multiple competing explanations circulated in the scientific literature in real time, some researchers favoring a simple cooling of the surface, others favoring an obscuring dust cloud, and the uncertainty itself became part of the story. The wider internet did what the internet does with uncertainty, and supernova countdown headlines multiplied well beyond what the actual data supported. It is worth remembering that this was not the first time skywatchers had reacted strongly to an unusual brightening or dimming of a star that turned out to be far less dramatic than first assumed. Records from multiple ancient cultures, including Chinese astronomers in the year 185 and again around the year 1006, describe sudden guest stars appearing in the sky, some of which modern researchers have since traced to actual supernova remnants light years away. The instinct to watch a changing star closely and wonder what it means is not new. What has changed is the amount of actual instrumentation now pointed at the sky to check that instinct against real data within months instead of centuries. The real explanation came a little over a year later, and it is more interesting than an imminent explosion. A team led by Miguel Montargès at the Observatoire de Paris and KU Leuven used the sphere instrument on the European Southern Observatory's Very Large Telescope, along with the gravity instrument on the same observatory's interferometer, to directly resolve the surface of Betelgeuse across the dimming event. Comparing images from before, during, and after the fade, they found that a patch of the star's surface had cooled, likely from unusual convective activity, and a bubble of hot plasma had been ejected from that region. As that ejected material moved away from the star and cooled further, it condensed into a cloud of solid dust that partially blocked our view of Betelgeuse's southern hemisphere from Earth's vantage point. In plain terms, part of the star was hidden behind smoke it had just exhaled. The research was published in the journal Nature in 2021, and it closed the loop on what had briefly been the most talked about star in the sky, resolving the debate between the cooling hypothesis and the dust hypothesis by showing that both were involved. That would have been the end of the Betelgeuse story for most people, except the star kept doing something else that had puzzled astronomers for a very long time. On top of its 420-day and roughly 6-year cycles, Betelgeuse has a long secondary brightness variation that researchers had debated the cause of for well over 100 years. One leading idea was that a companion star, tucked in tight orbit around Betelgeuse, was responsible for that longer pattern, but actually seeing that companion seemed close to impossible. Betelgeuse is so bright and so large that any smaller star orbiting close to it should be completely washed out in the glare, the way a candle flame disappears next to a searchlight. In December 2024, a team led by Steve Howell at NASA's Ames Research Center pointed the Gemini North telescope in Hawaii at Betelgeuse using an instrument called ALIPEC, which captures extremely short exposures to freeze out the blurring effects of Earth's atmosphere, a technique called speckle imaging. They timed the observation for a date their models predicted would show the widest apparent separation between Betelgeuse and any hidden companion. The result, published in 2025, was the first tentative direct image of a faint companion star sitting almost inside Betelgeuse's glare. Researchers studying the find have informally nicknamed the companion in some of their own writing, though it still lacks a formal agreed-upon name in the scientific literature. The detection was not overwhelming on its own. The team describes it as a low confidence signal on the order of 1.5 standard deviations, but its position, brightness, and estimated mass lined up well enough with theoretical predictions that most astronomers studying Betelgeuse now treat the companion as real rather than speculative. It solved a mystery that had sat unresolved since before Herschel first noticed the star's brightness changing at all. That companion star turns out to matter for a completely different reason than most headlines gave it credit for. Models of its orbit suggest it is gradually being pulled inward by Betelgeuse's gravity through tidal interaction, and it is expected to eventually be swallowed by the giant star's outer atmosphere, likely within roughly the next 10,000 years, well before Betelgeuse itself reaches core collapse. Far from being a sign that something dramatic is about to happen to Betelgeuse soon, the companion's discovery actually pushed some of the more aggressive short-term supernova predictions further out, because it gave astronomers a second independent way to check their models of the star's internal structure and evolutionary stage against something predictable and physical rather than just brightness fluctuations alone. The next, especially good window to study the companion directly is expected around November 2027, when the two objects are again predicted to reach their widest apparent separation, and researchers are already planning observation time for it. Until then, the companion sits right at the edge of what current instruments can resolve, which is exactly why the original detection came with that low confidence caveat attached, and why follow-up observations matter so much before anyone treats its existence as fully settled science rather than a strong, well-supported candidate. If you have made it this far, here's the quick version of where we stand before we get to the actual Webb discovery, since this is a good moment to reset before the most important part. Betelgeuse dimmed because of dust, not death. It has a barely confirmed companion star that is not a warning sign but a scientific tool. And the star that James Webb genuinely did catch near its final moments this year is not Betelgeuse at all. Stick around, because this next part is the actual reason this video exists, and it is a better story than the fake one. In June 2025, a survey called the All-Sky Automated Survey for Supernova A picked up a new stellar explosion on the 29th of the month, cataloged as SN 2025 PHT, inside a spiral galaxy called NGC 1637, roughly 40 million light-years from Earth. That is an important detail to sit with for a second, because 40 million light-years is a completely different scale of distance than the 550 to 700 light-years separating us from Betelgeuse. This supernova has nothing to do with our own night sky's Orion. What made it significant is what astronomers already had on file for that patch of the galaxy. A team led by Charlie Kilpatrick at Northwestern University realized that James Webb had already imaged that section of NGC 1637 before the explosion happened, and so had the Hubble Space Telescope on separate occasions. That gave the team something astronomers almost never get, a direct look at the exact star that exploded, taken before it exploded, which they could then compare against images taken after the blast. Combining the Webb and Hubble datasets, the team identified the star's progenitor at mid-infrared wavelengths for the first time in the history of supernova research. The progenitor turned out to be an extraordinarily dusty, extraordinarily red supergiant, roughly 100,000 times more luminous than our Sun, but so thickly wrapped in its own shed dust that it appeared around 100 times dimmer in visible light than it actually was. Webb's infrared vision could see straight through that dust in a way that optical telescopes simply cannot, because infrared light passes through fine dust grains that scatter and absorb shorter, bluer wavelengths. According to Kilpatrick and co-author Aswin Suresh of Northwestern's Weinberg College of Arts and Sciences, this is the reddest, dustiest red supergiant progenitor ever confirmed exploding as a supernova, and it helps answer a puzzle that had bothered astronomers for years. Stellar models predict that red supergiants should make up the majority of core collapse supernovae in the universe, yet for decades, observers kept finding fewer actual progenitor stars in their pre-explosion archival images than the statistics said should be out there. This result, published in October 2025, points to an answer. Some of the missing progenitors were never missing at all. They were simply too wrapped in their own dust to be seen clearly by earlier generations of telescopes working mainly in visible light. Webb's ability to peer through that dust in infrared light is opening up a category of dying stars that used to be functionally invisible until after they had already exploded, and the team behind this discovery is already using the same method to hunt for more hidden progenitors in other galaxies Webb has previously surveyed. Kilpatrick has been public about how long this specific kind of discovery took to arrive, noting that astronomers have been trying to nail down exactly what red supergiant explosions look like for decades, and that it took Webb's combination of sensitivity and infrared reach, paired with sheer observational luck and already having pre-explosion coverage of that patch of sky, to finally get a clean answer. That hunt is about to get a lot bigger, too. The Virasey-Rubin Observatory in Chile, which began its main sky survey work recently, is projected to catalog somewhere between 3 and 4 million supernovae over the course of a decade, simply by repeatedly photographing huge swaths of the sky and flagging anything that changes. Historically, astronomers have estimated that a galaxy the size of the Milky Way should produce a supernova roughly once every 50 to 100 years, yet we have not confirmed one inside our own galaxy since 1604, which strongly suggests that interstellar dust has been hiding a number of these events from optical telescopes the entire time. Between Rubin's sheer survey volume in visible light and Webb's ability to see straight through dust in the infrared, astronomers now have, for the first time, a realistic shot at catching the next galactic supernova candidate early and studying it properly instead of stumbling onto its aftermath centuries later the way Kepler did. That is the real story that the fake headline about Betelgeuse is almost certainly a distorted echo of. Someone, somewhere, took a genuine and well-sourced Webb discovery about a red supergiant's final moments in a galaxy 40 million light-years away, and swapped in the name of a much more famous, much closer red supergiant to make the headline hit harder. It is a pattern worth recognizing because it shows up constantly in space content online. Take a real discovery, Keep the dramatic language, replace the actual subject with whichever star or planet already has an audience's attention built in. So why does any of this actually matter if Betelgeuse itself is not the one that exploded? Here is the concrete, defensible answer. The technique Kilpatrick's team used, comparing archival Webb infrared data against post-explosion images to characterize a progenitor star in detail, is now a proven method rather than a theoretical one. It means that when a star like Betelgeuse does eventually go supernova, astronomers are no longer starting from scratch the way they were for events like Kepler's supernova in 1604, which was studied entirely after the fact, with nothing but naked-eye records to work from. Webb has already built a track record of identifying exactly what kind of star exploded, how much dust surrounded it, and how bright it truly was beneath that dust, using data collected before the explosion happened. If Webb or a similar infrared observatory has usable pre-explosion data on Betelgeuse by the time it finally does collapse, researchers will be able to apply that same before and after comparison to one of the best studied stars in the sky, turning what used to be pure guesswork about a star's final internal state into something closer to a documented case study. That does not rewrite anything about when Betelgeuse will explode. What it changes is precisely how much we will actually be able to learn the moment it finally does. There is a second, quieter reason this matters, and it has nothing to do with dramatic explosions at all. Stars like Betelgeuse spend the final stages of their lives constantly shedding material into space, the same kind of ejected gas and dust that caused the great dimming in the first place. That shed material is not waste. It is the raw supply chain for the next generation of stars, planets, and eventually, life. Every atom of calcium in your bones and iron in your blood was forged inside a star that lived and died long before our sun ever formed. And red supergiants like Betelgeuse are one of the primary factories still running that process today. Studying exactly how and how much material a star like this releases before it explodes is not just an academic exercise about one famous star. It is direct, ongoing research into the manufacturing process behind the raw materials the universe uses to build everything else, including us. As of today, Betelgeuse has not shown any of the signals that scientists would consider genuine evidence of an imminent core collapse. A 2023 study analyzing the star's carbon-burning pulsations raised the possibility that the timeline could be shorter than previously assumed, phrased by its authors with appropriate scientific caution rather than certainty, and it briefly fueled another wave of supernova speculation online at the time. But the companion star discovery in the years since has generally supported the longer end of the estimated range, with most current research still placing the likely explosion window somewhere within the next 100,000 years, a span that is short by the standards of stellar evolution and functionally unpredictable by the standards of a single human lifetime. Betelgeuse today continues its ordinary variability, brightening and dimming on its established cycles, with no dust-veiling event on the scale of 2019 to 2020 repeating so far. Researchers are watching for that November 2027 observing window to get a better look at the companion star, and continuous photometric monitoring from both professional observatories and organized amateur networks like the American Association of Variable Star Observers keeps tracking the star's brightness night by night, feeding into a database that now spans well over a century. If you want to check on Betelgeuse yourself between now and whatever comes next, it is genuinely one of the easiest bright stars to find, sitting at the upper left shoulder of Orion for viewers in the northern hemisphere winter sky, easily located with any basic stargazing app just by searching its name and pointing your phone upward. If Betelgeuse does eventually go supernova, the actual physical signature would look almost nothing like what circulated in that fake headline. The very first warning would not come from a telescope picking up strange infrared spikes weeks in advance. It would come from neutrino detectors, instruments built to catch nearly massless particles that stream out of a collapsing stellar core hours before any visible light from the explosion reaches us, since light has to fight its way out through the star's outer layers, while neutrinos pass through almost unimpeded. This is not theoretical. It already happened once in 1987 when a supernova in the Large Magellanic Cloud called SN 1987A became the first supernova ever detected through its neutrino burst, arriving hours ahead of the visible light and confirming decades of core collapse theory in the process. That single event, close to 160,000 light-years away, remains one of the most studied supernovae in modern astronomy precisely because instruments were finally sensitive enough to catch it in nearly every part of the spectrum, from neutrinos through visible light to X-rays, giving scientists their first real direct test of what theory had predicted for decades about how a massive star's core actually collapses. Some astrophysicists, including Michael Schara at the American Museum of Natural History, have publicly proposed building a dedicated neutrino detector specifically capable of giving days of advance warning before Betelgeuse's light actually arrives, precisely because that early neutrino signal is the one genuinely reliable precursor science currently expects. Once the visible explosion did arrive, models built by researchers including Evan Goldberg and Jared Bauer suggest it would shine roughly as bright as a half moon for weeks to months, visible even during daylight, casting shadows at night, an event with no precedent in recorded human history at that close a range. For comparison, the last supernova definitively seen with the naked eye inside our own galaxy was Kepler's supernova in 1604, observed by Johannes Kepler and his contemporaries more than 4 centuries ago, before the telescope had even been invented, and there has not been another one confirmed inside the Milky Way since. Statistically, based on how often galaxies our size are expected to produce these events, we are considered overdue for another one, and a Betelgeuse supernova, whenever it finally happens, would be far closer and far more thoroughly instrumented than anything observers in 1604 could have imagined. And despite how dramatic that all sounds, it would pose no danger to life on Earth. Research on supernova radiation effects generally places the harm threshold at around 160 light years, and Betelgeuse sits well beyond 3 times that distance. What remains genuinely unknown is specific and worth naming honestly, rather than dressing up. Nobody can currently predict Betelgeuse's explosion date within any range narrower than tens of thousands of years, and that uncertainty is not a gap in effort. It reflects real limits in how precisely stellar physicists can model the final, chaotic stages of a massive star's core. The companion star's exact mass, precise orbit, and eventual fate still carry real uncertainty, which is part of why the November 2027 observation window matters so much to researchers working on this. Upcoming instruments are expected to help narrow these gaps. NASA's Nancy Grace Roman Space Telescope, designed for wide infrared surveys, and the European Southern Observatory's extremely large telescope, currently under construction in Chile, are both expected to add new observational power to red supergiant research in the coming years, potentially giving astronomers even more precise looks at stars like Betelgeuse's companion and at other dust-obscured progenitors similar to the one behind SN 2025 Poblaci. Whether Webb specifically will have enough pre-explosion infrared data on Betelgeuse itself, positioned the right way, at the moment it finally does collapse, is not something anyone can guarantee, since that depends on decades of future telescope scheduling that has not been written yet. The strangest part of this whole story, once you strip out the fake urgency, is the delay baked into the light itself. Every photon of Betelgeuse you have ever seen left that star centuries before it reached your eyes. If Betelgeuse had already exploded 500 years ago, we would not know it yet. If it explodes tonight, most of us alive right now will likely never see the result, because the light needs centuries to cross the distance separating us. The star hanging on Orion's shoulder every winter is not a live feed. It is old mail, arriving on a schedule none of us control, and the honest version of this story is not that Webb caught Betelgeuse dying. It is that somewhere out there, in real time, that star is already living out whatever comes next, and we are simply not there yet to see it. What Webb actually proved this year, out in NGC 1637, is that when the light from a dying star finally does arrive here, whether that star is 40 million light years away or 550, we now have the instruments ready to read it properly the moment it shows up. That is a far better ending to this story than a fabricated photograph of a shoulder in Orion that never existed. It is a real capability, built and tested on a real star, waiting for whichever star, including possibly Betelgeuse itself, sends its light our way next. If this kind of fact-checked deep dive is useful to you, subscribing means you will not miss the next one. Drop a comment with which part of this surprised you most, the companion star or the real Webb discovery in NGC 1637. And if you know someone who shared that fake headline, sending them this might save them the embarrassment of sharing the next one.